Now, it perhaps bothers you a little bit to have to say that the reflection, that all this is happening, that there's reflections from all this part of the mirror when all it does is cancel out. And so let's discuss this a little bit. Let's do an experiment to find out how much light is reflected under similar circumstances. And I guess since I have one more color, and I don't want to erase everything I've got there, let us just imagine, for definiteness, that only this, well here, let's say this piece of the mirror, I just used a piece of mirror so big, no bigger, I just used a little piece, it's a big piece, but it's in the wrong place. And I expect to see the light reflected from here to there. Not very likely, huh? But this dopey physics says that, yes, you have to calculate all the arrows from all this stuff from here to here, and they're all changing. It corresponds to the arrows up to there from the beginning. So it's just a bunch of arrows that go zzz, zzz, zzz for a while, and I stop, okay? You know, that line means these arrows are not in the picture anymore because that part of the mirror isn't there. And so you see that the distance from where I started to where I finished is very small. Not zero, but very small. And it's true. Experimentally, with a finite piece of mirror, you get a tiny amount of light reflected in an odd manner. It's called diffraction from the edges, but I don't want to go into that. It's very tiny, so let's say it's zero. This idea that the whole thing can be there and doing nothing seems like a kind of a waste of time and a mathematician's thing only. It's not real physics to have something that's not doing anything. But watch this. They're going to prove that it's right by the following dirty trick. I perhaps should expand this side a little bit. I'm getting pushed off the side of the board there by the way I've drawn it. This is the way the time was going, and the arrows were pointing in a sequence of directions which were very different from one another. And now I'm going to do a more fine calculation, which I cut it even finer, and you would find, if it's fine enough, that I haven't got much difference in time, but I find a bunch of arrows essentially going around in a circle, very close to a circle, getting nowhere, going around and around in a circle, because some of them are pointing forward and some of them are pointing backwards virtually, it's continuous, but for some contribute this way and some contribute that way. Now let's have some fun. Let's see if it's really true. What we're going to do is we're going to make the mirror less effective by painting it black in the right place. We're going to paint the mirror black in just those places in which the arrows are pointing the wrong way. For arrows, if it turns out that the timing is such that the arrow points this way, don't use that part. Paint that part of the mirror black. Don't use it. Make it not reflect. I don't painted the wrong curve. I should have painted. My drawing is unfortunately way over here. The idea is, if the arrow is this way, I take it. But any time the arrow comes out that way, if that's the time between here and here, then I paint that part of the mirror black so that those arrows don't operate. In other words, in order to test this idea that everything's canceling out, I take the parts of the mirror for which the timing is just right to make arrows that point this way, or more or less that way, or at least have a bias in that direction. And the parts of the mirror that were contributing arrows whose bias was in this direction, I paint out. Or, if you don't like this idea of painting out, and you have enough patience, you simply cut the silver away. There's nothing. The light goes through. Worse, it can't reflect. It didn't reflect before. You got less mirror. It's going to reflect less. No, it reflects perfectly well. Because according to this picture, if I add a sequence of arrows which are turning rapidly, and then as soon as they're supposed to come on, oh, here's the circle. Here it is, down here. Excuse me, and it's also in yellow. I add the arrows this way. They're going along all right, and as soon as they start to turn back, I don't let it go. I don't add anymore. I've cut the silver away. And now it gets around and starts to go in the forward direction again. So I let them come. I don't paint that silver away until it starts to back up, and then I paint the silver away. I get it out. And what I end up, of course, is a lot of little strips of silver separated by clear glass. And each time the thing does this, bloop, bloop, yeah, bloop, 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 bloop. over this whole distance, and wow, what a net arrow I've got for the final result. Lots of light. And so it's possible to take an ordinary mirror, flat, and cut away strips correctly in the right places, just right, strip after strip, very fine, it turns out, thousandths of an inch. So that when you shine light down on it this way, it bounces it off that way. This thing would only work with one color. If I've designed this it's called a grating. It's a line of lines, and it works like a charm. It's beautiful. If I use red light, and I've got that thing exactly right, it'll go right. If I use blue light, it won't work. What I had forgotten to tell you in the beginning, and I don't know whether I said it last time, is this is what happens with red light. With blue light, you get the same result, except the thicknesses are shorter. All the timing is quicker. And what the rule is for blue light is the same as it is for red light, except the speed at which you turn that for time is faster. You turn it more. Now you'll notice that the place that we put those cuts was especially designed just for this rate of turning. If it turned a little more, because it's blue, and I had the cuts in the same place as I made for my theoretical red one, it turns out it all gets kinked up and it doesn't work very well. But as a matter of accident, it happens to be so that if I make two changes, first I use blue light, and then I put the photomultiplier at a somewhat different angle, in fact less angle, it works again with the same lines that I used for red. It's an accident. I cut it carefully for red, put that photomultiplier over there. It also happens, luckily, that if I change the color, it doesn't work. But if I move the photomultiplier and change the color, it's cut again about the same place. It comes out, just geometry. And therefore, what happens is actually that if you shine light down here, blue light will come over here and red light will come over there, and it's a beautiful thing to see. Because if you take this thing and turn it, when the light is fixed, you'll see colors, red and blue. I don't know whether it's come down in New Zealand or must have. We have them in the United States now on automobiles. People have these wonderful colored signs that you wonder where the colors come from. They're so bright, and as the car moves, it changes from red to green to blue, and all they are is mirrors with lots of lines on them instead of, so they're not reflecting in the normal manner. All right, so that shows really that we cannot get rid of the area which gives zero, that it really is canceling out, and if we do torturous and clever things to it, we can demonstrate the reality of the reflections from this part of the mirror and produce some striking optical phenomena. It depends on how much of your experience is, whether this appealed to you or not, if you knew about gratings or you didn't. That's the problem with this lecture. I can go on like this explaining holograms and lasers and everything else easy, except you don't know anything about them. There's no use, but never mind. I'll try something else. This time I'm going to talk about light going from air to water. We would like to put the photomultiplier under water. We'll suppose the experiment, they're going to arrange that. This is water. Maybe it's easier to put the source under water. And here's the source of light that we would like to know. Photons, have a small number of photons. We want to know if they're going to get there. And we have, again, the same situation, that the light can go this way to the water surface, and then that way to the photomultiplier, or it can go this way to the water surface, and that way to the photomultiplier, and it can go all different possible angles. And every one of them contributes an amplitude, and it makes a bunch of arrows at all different kinds of angles, and what's going to be the result? Same picture as we made up there. The only part that really gives a result is when the time is changing slowly. In other words, it's a minimum or a maximum. Minimum. Now, in this particular case, in water, I didn't tell you about this, but in water, when you're finding the amplitude, the rate at which the thing goes around in water is slower than in air. Or better, maybe it's a better way, excuse me, better. I made an error. What I said was wrong. Light travels slower in water than it does in air. So that the time, when you calculate for a length in water, is not the same as in air because the light goes slower. So that these lengths are more important, so to speak, than in here. What you need to do to find out what's the most important of these pairs. Remember, as before in the case of the mirror, many of them all canceled out and didn't make any difference, but there were some that were important when the arrows were always the same, when the time was minimum. So what we have to do is we have to figure out to go in here and to come down here where the time is minimum. The idea is, suppose that you were really in water, and you went in a boat. You could only go slowly, and then you could run quickly on land. Well, the beautiful girl is drowning here, and you're the lifeguard, and you can swim slower in water than you can run on land. Where do you hit the water? You rush this way to the water and swim like hell. No. Actually, there is a place that's the minimum, which it would be foolish of a lifeguard to analyze and calculate under the circumstances. But the fact is, there is a computable position at which the time is minimum, and it's some kind of a thing that looks like that. The idea is, it is not the straight line, because the straight line has too much water in it, so to speak, water path, and by moving for less water path and more land path, one makes a compromise and comes out so. And that is the reason why light is bent into water. And as a matter of fact, if you follow this thing all the way through, you can prove that the ratio of the sines of the angles of the this and the that is the ratio of the speeds in the air and the water. But the reason that it's a minimum time is the same reason as it was for a mirror. Okay? In the same way, we can understand why light goes in a straight line. It's usually, if we had a source here and a photomultiplier here, there are many ways the light could go. We could say the photon can go from here to here, a certain amount of time, phase. That's the way I've been doing it before anyway. But I'm going to be more accurate this time and tell you that the story that I said it went in a straight line before and calculating things was only an approximation. If I didn't do that, I get the same answer as if I do the following. I say, not only does it go in a straight line, it could also go this way to here. It could go this way to really? Really? It can really do it? Yes. It can go any way it wants. But almost always, the contributions from these different ways cancel out with each other completely because there's a nearby way that's got the arrow the other way. But if you can find a way where if you change the paths a little bit, nearby paths, don't make any difference to the time, then you've got the place where most of the contribution is coming from. And the story is as follows, that if you have a path like this, the nearby path can be made that's shorter. That is, has a different time. Distinctly shorter, a lot shorter by moving it in. And so you get a very different time. But that the minimum time comes for the path that's a straight line. And so the most important contribution is from the straight line. Remember that in the case of the mirror, I say the most important part of the contribution is near the place that is the minimum. It isn't exactly that one arrow that does it. No, it's the contribution over quite a range. And so it turns out that a light does not really go in a straight line, but it smells the neighboring lines and it uses area around it, just like a section of mirror is necessary to get the full reflection. A section of space is necessary. If you were to put blocks in here so as to not allow the path to wander too far away, and made these very tight so that it was try to go in a straight line, you would discover that the light from this source, if you put the photomultiplier here, for instance, and didn't have these blocks, no, if you put these blocks in like this and had the photomultiplier here, let's say the blocks are pretty far apart, and put the multiplier in such a way that that line is not allowed, that corresponds to using the piece of the mirror that's in the wrong place. But if this thing squeezes tighter and tighter, after a while light begins to come here. The reason it comes is that you've only got a few of the arrows. It's just as if you used I didn't show you in this case, the same idea. If you did have the mirror in the wrong place but used a very short mirror, then there's not enough range for the arrows to cancel each other, just a few that go one way and it stops. And so what happens is that there's a little, if you cut this very fine, the light spreads, that it doesn't go in a straight line. And if you try, therefore, to squeeze light into a small hole to make sure it's going in a straight line, you discover that it no longer goes in a straight line. This is a few examples of how the theory of thing is worked out. Let me just do one more, which is interesting. Instead of dealing with all the net result of adding all these, in the empty space, of adding all these different possible paths, is in fact turns out to be the same as if you just took this one path. Very closely, as we for approximately, well, essentially that. I mean by that there's just another factor. The angles are the same. If we think about this in a special case, let's draw an artificial line here that means nothing. It's just like the equator of the Earth. It's just a line. And then consider paths which are straight in two sections. Then ask, what about light going this way, and this way? So you don't have too many different paths to add. We restrict them to be double straight line sections. Then by exactly, the answer is exactly the same as for the case of the mirror. The time to go this way is a big time, and this changes and changes, and it changes rapidly. And if I plot it this way, the time for these different things, this is a long one, that's a short one, that's a long one. This time you can figure the time immediately in your head, because the time is just the length of that line, and you can see that that's long and that that's short. Now, let's have a different kind of a game. Let's do something to make this one longer so that it's the same as that one. Let's fool the light so that all the paths are the same length of time. How can we? I told you it went slower in glass than in air. So let's put a piece of glass in here to slow it up so as to take a little longer. Let's say we're not going to do anything to the path out here. That's going to be the key time that we're going to make everything equal to. Now the one that would go through here straight would have got there too fast. We slow it up for a while, and by slowing it up, we bring it so that the time it takes is the same. Now there was a path that went like this, and that had a time so. It's also too short, not as much as the other one. We have to make it take a little longer, so we have to put a piece of glass in here. This glass is not as thick as this one because we don't have so much to offset. The nearer we get to the top, the less we have to use glass to slow it up, and the very last one needs no glass at all. When you put all these funny pieces of glass in there, the net result, of course, is that you're putting in a piece of glass shaped like so. The result of that is that the time, now, with the glass in, by careful design and the exactly right shape and right thickness, you just found out how to calculate the thickness exactly, just put the right thickness in to compensate the time, you will find that the times now are all the same, no matter which path it is of these straight line types. What happens then? Now, each one of them contributes its amplitude. Yes, amplitude, same time, same, whatever the angle of one of them is. The next one's the same, next one's the same. You straightened out the arrows. What a dirty trick. You straightened out the arrows. And there's a lot of arrows. There's millions of arrows. And so the result of this is that they get, for the final result from the front to the tail, a sensationally large, unexpectedly enormous arrow, a high probability of going. Of course, you know what I'm describing, a focusing lens. If you have a source of light here, and it just sends light to here, it's kind of weak because it spreads. But if you put a lens here, it'll concentrate it right away again back to here. And that means concentrated light means high intensity, and really high intensity means lots of photons. Or if the light was weak, the chance of a photon arriving is very strong at this particular point and very small everywhere else. And so by the trick of arranging things so the times are equal, we focus light. And so by this, I use these examples to show you how what looks at first like an absurd rule with no causality and nothing like anything real produces effects that you're more used to. It also produces other effects that you may not have been used to, such as the grading and a number of other things. And so this is the success of this point of view, and it continues to be successful. And I would summarize it by saying what we know so far is that the probability is equal to the square of an amplitude, then they need a calculus of the amplitude, that an amplitude for an event that can happen in several different ways. In different ways, I should have written this in the beginning, is the sum of an amplitude for each way. Now I have the rest of that should be really all that is really necessary to understand. But in order to get a full flavor of the theory, I would like to tell you a little bit more about how people calculate these amplitudes. And a little bit more about the law for the amplitude. For example, I kept bringing in funny things like, when you have a reflection, you have a little arrow. When it's from the other surface, you make the arrow backwards. When you go through glass, you have to use a faster timing, and so forth. All right? All these things should have to be explained, and they will be, not this lecture. However, the particular feature that I can describe a little better, a few things of how we analyze the amplitude. A particular problem, to show you the type of thing, is this. Suppose you had a surface here, and that we have a reflection. Suppose this was a 4% surface, so that the amplitude, the intensity that came out here was 1/25th, but that for that surface, the amplitude of reflection is a fifth. Now that, and I put the photocell here. Well, you could put a double surface. Oh, I have it already drawn. I'll draw it again. I have a double surface, and the source, and the reflections, and all this stuff, and I computed the amplitude for the light to arrive here. Now I'm going to try another thing. Instead of putting the photomultiplier there, I make a little hole, I let the light keep going, and I let it bounce through a couple of other surfaces, 3 surfaces, whatever it is, all right? And come out over here and put the photomultiplier there. How do I figure out what happens, what the amplitude is? Now this amplitude in this particular thing can be thought of in, as so to speak, 2 problems. One, if light starts here, what's the amplitude to get here? The second, another problem that's interesting, is if I put the source here directly, what would have the amplitude to have got there been? It turns out, from those 2 things, you can figure out this combined problem by an operation you could call the rule for successive amplitudes. Right? The rule goes like this. Let us suppose that this section here, if you don't understand this too well, it doesn't make any difference. You get some, I'm trying to give you some flavor. The flavor tastes bad. It is, just relax. Now here, some people like ginger snaps and some don't. Let's say this problem, we've already worked out the amplitude for all the possibilities added together to arrive here. Let's call this point A, this point B, and this point C. So we have the amplitude to get to B from A. That is, a source A of unit strength, 1 photon, has an amplitude to get to B that's been worked out. Let's suppose we start out, this is the source strength, 1 unit. We begin. And what do we get out is the result B, the amplitude comes out some crazy arrow. So let's say that that thing is this arrow. That's the amplitude that gets from B to A with the source. What is this thing? It's 1/5 as long. Let's say it was 1 surface. It's 1/5 as long and a certain timing. Let's suppose this surface over here ends up as a 4%, 1/16th reflector, or 11%, and 1/9th reflector. Makes it easy for me. The length of this thing is a fifth, you see, so that the thing will be 25, 1/25th, and you have to turn it through an angle. Now this next one, if it would work all by itself, if the amplitude to get to C from B alone is this. If at B there was a unit amplitude, if at B it really was 1, then there's a certain time delay and the reflection. There's some time delay corresponding to some angle, and there's a length of 1/3. This happens to do with the time delay. The time delay, I mean, from B to C. Now, what would the result be? Why do I say 1/3? Because the area of the square would be 1/9, which is how I said the reflection should be. Now, what will be the amplitude to go get to C from B, from A, all the way? It isn't hard to guess. First of all, the total time means that the angle, whatever it is, you go around and around and around, the sum of the amount you went around for the first part plus the second part, because the total time is the sum of the 2 times. So that they're going to draw something whose angle is the sum of this one and this one. It would have turned around while it was going to B. It goes around, 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 around. It goes to B, and it goes around, 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 around some more, and that's how much more. So the net result is an arrow sum like this at an angle, which is the sum of that angle and this one. You turn this, and then you turn it that much more, and you come to here. Here's where we start with the 1, and here's what we're coming out with. And how long should it be? Well, the chance that it gets, of all the light that comes down here, 1/25th is reflected here. And of all the light photons that come here, only 1/9 is reflected there. So it turns out that that means that of the light, let's say I had 1,000, well, I have bad numbers. I should have taken better numbers. What you have when you finish is 1/25th times 1/9 of the light. 1 over 225 parts out of 225 photons. About, on the average, 1/25th or 9 photons get through here. And of those, 1 goes here. So 1 out of 225 come out, which is, by the way, 1/15th times 1/15th. 15th. So therefore, this size of this is 1/15th. Now, the 1/15th can be, this composition, this is the rule of composition. Add the angles and multiply the length. So you have two events in succession. You combine them by this rule of composition that you add the angles and multiply the length. Putting an arrow on the tail of another arrow to find a final arrow, we call adding the amplitudes. Composing them this way, multiplying their lengths and adding the angles, we call multiplying the amplitudes. The reason we call it multiply is interesting, therefore, that arrows can be added, can be combined by two operations, putting them on each other's tail and multiplying them together like this, which we have called adding and multiplying. And the reason we call it adding and multiplying is it obeys all the right rules of arithmetic for addition and multiplication. All of the rules such as, I don't remember the rules. A times B is the same as B times A, for instance. A and B are these arrows, combining it this way and meaning by times this composition rule, then it continues to be right. Now, the rules of algebra are things that are studied by mathematicians, and mathematicians have tried to find all the objects that you could possibly find which obey those rules. The rules were originally made for counting apples. It was improved by using negative numbers. It was improved still further by inventing fractions. It's still true you can add and multiply fractions. You can use unending decimals to represent numbers and add them and multiply. We have today become very sophisticated. In the early days when mathematics was first developing, and it was said that a number is something like when you count the number of apples or people or something like that, then the whole idea of a half a person was a problem. But today there's no difficulty at all, and nobody has any moral or discomforting, gory feelings when they hear that there are 3.2 people per square mile in certain regions. It doesn't bother them. They don't try to imagine the 0.2 people. But what they do is they know what they mean, that if they multiply that by 5, it gets to be 16, and so forth. And so some things that can satisfy the rules of arithmetic can be interesting to mathematicians, even though they're not represented by numbers of apples, absolutely, and without having to picture exactly what it is. And these arrows on a plane, which can be combined by two operations, tying them on each other's tail and combining them by this multiplying and adding angle business, those two rules, adding and multiplying, obey the same rules as algebra, and these amplitudes are in fact called some kind of numbers by mathematicians, and to distinguish them from ordinary numbers, they call them complex numbers. Makes it hard, in other words. So for those who have studied 4 years of university or enough algebra to have come to complex numbers, I could have said all this by simply saying amplitude, the probability is the square of a absolute square of a complex number. The amplitude is a complex number, and the probability is its square, and that when the thing can happen in more than one way, you add the complex numbers, and when it happens in succession, you multiply the complex numbers. And have I said any more than I did before? No. It's just a different language, and it may sound better, and the only reason I use that different language is because some few of you may have heard of that language, and it would be nice to make sure, I just wanted to make sure to you that it was really the same thing. For those who have never heard of it before, the idea that that is multiplication may be disturbing, and I think I waste a little time on the side. It has nothing to do with, well, I think I waste time. I'm late, so I shouldn't waste time. I wanted to explain why it's reasonable. I can't resist. I want to explain why that is a reasonable way to define multiplication. This is a stupid thing. It has nothing to do with our lecture. I call it multiplication. That's enough. But I have to play it anyway. what is a multiplication? And the Greeks used numbers, wanted to use numbers that were not necessarily integers, and they did it by talking about lines. If this is a unit, then the line, this length, represented the number 1. Whereas a number like 2 would be represented by a line which would be twice as long. That way you can represent fractions and so forth. The third is long, 2.5 times long, so forth. So here's 1. 2 is the relationship of this line to that. Now 3, you might get the relationship of this line to that. All right? I have to write the unit. In order to understand what this number is, I have to tell you how big 1 is. Now what's 6? The product of 2 and 3. It's a line also. It's a line that sticks way out. And it's like so. It's got 6 notches, already 6 notches. And the way of looking at it is to say that the problem is this. I want to convert 3 to 6. I want to multiply by 2. The idea is that the 3 line that I had before bears the same relationship to the answer that I'm trying to get, the 6 line, as the 2 bears to the 1. 6 is twice 3 in the sense that this relative to that is the same as the 2 to 1. Right? The idea is then that the answer should bear, of multiplication, should bear the same relationship to one of the things you're trying to multiply as the other thing does to the unit. Voila. Let's see. I want to multiply this by that. And what I have to do then is to create a line which bears the same relationship to this line as this one does to that. Yes? I have to, just like I did over there, I have to find a new, this answer has to have the same relationship to this line as this has to that. Now let us draw the answer that I drew over here, so you can see its relationship to that line. What's the relation of this and this? The relation of this and this is a certain proportion in size and a certain angle. Can you imagine that thing turned so it's in this, and you see that it's the same angle and the same proportion as the original 1/5 to 1. In other words, the relation of this line to that is the same geometrically. And so that's why it's multiplicative, because it has the same geometrical property, a property, though, that fits on lines which are tilted, not just lines which are horizontal. It's interesting, the mathematicians developed all this mathematics with these crazy numbers without having anything to apply it to directly in physics, and that it should turn out to be so fundamental to the bottom laws of physics to be using such funny numbers or complex numbers. So that's the other feature. And I'll just say one more thing to finish this. That means that we can understand what happens in a given situation by a sequence of, as if it's a sequence of events. Instead of, you see, when I was talking before, I would say the thing comes from the source and goes to the photomultiplier, and I gave you the answer for one operation. You turned it and you made a little line. But I can talk about it in several operations. I could say it goes from here to here. You start with an arrow. When it goes from one point to the other, just turn it around according to the time. Reflection. Reflection is a little 1/5 arrow. Multiply by that. That means shrink it down. Next, go from here to here. That means take the result and do again the same next thing, which is rotate. Now, finally, I would like to say, what I'm going about to say is to show you that we have still simpler laws than the ones that I talked about. We have been talking only about one color light and talked about the amplitude depending on the time in that fashion. What is the difference between one color light and another color light? The speed at which that goes around. But in space, light is light is light is light and doesn't know where it came from. And what another picture is, different picture is this. That light, if you want to know the amplitude that it arrives at a certain time, we're going to put time into this argument now. It arrives at a certain time in a photomultiplier. Well, suppose, well, I think, since I haven't figured out, I'm sorry, this is very amateurish, isn't it? I haven't figured out what I'm going to talk about completely next lecture, and I haven't got quite enough stuff to fill it up. And therefore, I'm going to leave this little thing for the next lecture so I can fill it up. I will tell you what the idea is, that the time has to do with the, well, I'll discuss that the next time. The other thing is, I have tried, and in the case of monochromatic light, I have completely described the rules for the amplitude. If I add one more thing, which I haven't, that is, I have to talk about what happens in a vacuum first. And when a light goes a certain distance, it's true that the angle turns, but there's another rule which I have not discussed because it's not very interesting relatively, and that is that the amplitude to go a certain distance, besides turning, shrinks. If you go far, it gets small. Everybody knows that the chance of finding a particle far away from the source goes down as a square of the distance. And that means that the amplitude goes down as the distance. In other words, when I was drawing these arrows, as I made them go further, I should have shortened them a little bit. Those are kind of approximations. They have nothing to do with the excitement of how it works, and I didn't want to bother you with such accurate detail. But if I once tell you that the thing turns at a certain rate and goes down in length proportional to the distance that it went, I have completely defined exactly the properties of the propagation of light of one color, except for one other technical thing. Light, as it turns out, even if you specify the color, I have to say this in order to tell you exactly, how much you know and how much I haven't mentioned. Even if you specify the color of the light, there's one other feature that light can have. There are two kinds of photons with the same color. We say they're polarized. If you use Polaroid, for example, you let through light that has only one kind of axis. And another piece of Polaroid lets through the same kind of photon. But if you set that other piece of Polaroid for its axis the other way, so that it'll pass light with the other kind, then no light will get through, where the first one only passes one kind and the second the other. All these effects of Polaroid and polarization have been entirely left out of this discussion. Why? Because my purpose is to give you a complete feeling of the difficulty of the subject, of the interesting philosophical problems about probability, the succession of amplitudes, how little we really understand, and so on. And the fact that there's two different kinds of photons is not qualitatively different. It just means a little bit more calculation, but of the same style. It doesn't change the style of the analysis. And therefore, in spite of the fact that I've left out a number of things, such as how the amplitude changes with distance, and the fact that there's polarization, makes my lecture incomplete in the sense that I therefore have not given you the exact law for the propagation of light. Not quite, but damn close, so close that it contains all the mysteries, all the peculiarities, and so forth in a perfectly satisfactory way. And I hope then that you're satisfied and you're confident that I haven't left any essential difficulty out. The things I've left out are not difficult. They take just another lecture of technical points rather than any new difficulty. One thing, though, I must say, and that is this. We've been talking about light going through a vacuum, and then I had a rule about it's reflected by a certain amount. When it goes, it has a certain shrinkage when it comes off a surface. When it goes through a medium, it gets slowed up, and so on. These, it turns out, are not really the properties of light that have to do with the properties of matter. You can't get reflection without having a piece of glass. It doesn't go slower unless it's in the glass. It really, as it turns out, is not going slower. It's curious, and we're going to find out exactly what it does. In order to explain it, we have to know what the electrons in the glass are doing and how they interact with the light. And I'll summarize the most wonderful fact is that light never does anything, really, when you get down to it, except go in a vacuum from one place to the other. It's emitted by one atom or particle and absorbed by another. And it never goes and gets slowed down or gets reflected. What reflection really is the light goes down, is absorbed by something which shakes it, and that emits a new light which comes back. Reflected light is really not the same photon coming back as went in. The photon from the source went into the glass, and from the glass comes out a new photon. This is an interesting thing that makes light in the end simpler and simpler and simpler. And what I was trying to get to in the last steps was to show you how ultimately simple it is when it's only in a vacuum. And the complications of funny laws for reflection and funny laws for going through glass are really the result of the interaction of light and electrons. And that's why this subject of discussing physics can't go on any further until I can discuss matter, and the next lecture will be about matter. All right? Thank you.